Okay, so we now have everything that we need to write down the answer for the Green's function using the residue theorem. So let's do that. So what is g of x comma y equal to? Well, there we are. G of x comma y is equal to. Now, first of all, let's take a look at the case where tx minus ty is greater than 0. So we will have a Heaviside function of tx minus ty. And now we should pick up the pole at minus omega p, because that's the pole that got shifted into the contour, okay? I'm looking over here. That's the pole that got shifted into the contour. And in the second case, when tx minus ty is less than 0, we'll be looking at the pole at omega p, okay? Good. So we want 2 pi I. So we'll have 2 pi I. And now we need to multiply by the residue. Now, just one other comment. We were integrating the 4p. We've just done the integral over p naught. So we will still have an integral d3p, and then we'll have the residue. And the residue at minus omega p is sitting at the top here. So we'll have minus I over 2 pi to the 4. We'll have e to the minus I omega p tx minus ty minus I p dotted into x minus y over 2 omega p. Good. And then there will also be a contribution when tx minus ty is less than 0, or equivalently when ty is greater than tx. Now, here I want you to notice something. In the first term that we wrote down, we went counterclockwise around the pole. But for the second term that we're just going to write down now, we are going clockwise around the pole. Because we go clockwise around the pole, we've reversed our direction of integration as compared to the residue theorem. So when you go clockwise around the pole, the answer for the integral will be minus 2 pi I times by the sum of the residues. So we'll have minus 2 pi I. And don't forget that this minus sign, so let's just make a little note, this minus sign is because we went clockwise, okay? That's why we've got that minus sign sitting there. We went clockwise around the pole. Then we'll again have an integral, d3p. And now we're picking up the residue at plus omega p. So what is that residue? Well, that residue is I over 2 pi to the 4. And then we will have e to the I omega p tx minus ty minus I p dot x minus y over 2 omega p. Good. So let's just tidy up these expressions a little bit. So we've got theta of tx minus ty. We have an integral d3p. We've got a 1 over 2 pi to the 4 times the 2 pi outside. So we land up with a 2 pi cubed. Good. Then outside, we've got an I, and in the integrand, we've got a minus I. So this I and the minus I, this I and that minus I, they multiply to just give us 1. So good, we've taken care of the I's. And then what do we have left? Well, we've got the exponential, e to the minus I omega p of tx minus ty minus I p dot x minus y over 2 omega p. Good. And let's just see. Yes, I think I've done that correctly. Then we've got plus the second term. Now, the second term is a theta function, a Heaviside function of ty minus tx. We've got a minus I outside, an I in the integrand. Those again multiply to give us 1. We've again got an integral d3p. We've got a 2 pi outside, a 1 over 2 pi to the 4 inside. So those again multiply to give us a 2 pi cubed. And then we've got e to the I omega p tx minus ty minus I p dot x minus y over 2 omega p. I almost like this expression. There's just one thing I don't like. Look at the exponential in the second term. This looks like an I omega p times difference in times minus I p dot x minus y. So that's omega p tx minus ty minus p dot x minus y. I like this very much because this looks like it is a p naught times by a delta x naught minus a p dotted into a delta x. And the time components and space components come with opposite signs. So I like that. Look at the first exponential. We've got minus I omega p tx minus ty minus I p dot x minus y. So the fact that we have a minus here and a minus here, that I don't like. I would have preferred it to look like the second term where we've got opposite signs for the first term in the exponent and the second term in the exponent. But we can fix that, okay? So we are going to do a change of variables. So let's just put that down. Good. So let's say, let's put it in blue. Perform a change of integration variable in the first term. And what we're going to do is we're going to change from p to a new variable. Let's call it p primed, and p primed is minus p. Now let's see what will happen. So omega p, which is p dot p plus m squared square rooted, because it depends on p dot p only, well, p dot p will be equal to p prime dot p primed. So this is omega p primed. So the omegas in this equation don't change. The other thing that we know, this is very easy, calculate the Jacobian, d3p is equal to d3p primed. So in actual fact, the only thing that is going to change is the sign over here. So that's all that's going to change, and that's what I wanted to change. Okay, so what are we going to do? Perform this change of variables, and once you've done it, rename p prime to p. Okay, so go ahead and do that. I think I've explained that pretty clearly. So I'm just going to write down the answer now for what we get. So what do we get? Well, finally things become theta of tx minus ty integral d3p over 2 pi cubed. We'll have an e to the minus I omega p tx minus ty. And now it's a plus because of this little change of variables that we've done. P dot x minus y over 2 omega p plus theta of ty minus tx, an integral d3p over 2 pi cubed. And then we've got e to the I omega p tx minus ty minus I p dot x minus y over 2 omega p. And if you look back at your notes, this is exactly the time-ordered correlation function of phi of x, phi of y, as we calculated it previously. So what that means is this is no longer a question. In fact, this is an equality. So the time-ordered two-point function really does agree with the Green's function. So we have just verified now that the path integral gives us the same result for the two-point correlation function as we got in the operator approach. So we verified this formula. Integral d phi e to the is phi of x, phi of y. And you could go ahead and study endpoint correlation functions. You now know enough to do that. And you could check that all correlation functions calculated in the free theory using operators and Fock space are in complete agreement with the same correlation functions calculated using the path integral. And one thing that was important here that I just want to stress is we had to use Feynman's I epsilon prescription. Okay, so that was important to get the agreement. Good. So that's all I wanted to say about the Green's function. This has been a long chapter all about the Green's function. We'll just have one more recording. I just want to quickly make a few comments on the exercises for this chapter.